Hello community, so great that you are back. Yes, today we have a fascinating video about the latest research by Google AI. And we look at small language models. Now, you know we have our titans, no? Our O3 Pro, Grok 4, super heavy, upcoming Gemini 3 Pro, GPT-5, and they all have beautiful reasoning, and they have implicit planning. So if we give them a task, they decompose the task into sub-goals before answering. And this is the ability that is a key driver here and the strong reasoning accuracy. So if we want to transfer this knowledge with imitation learning, what do we do? Well, easy, no? Extract complex reasoning traces and extract here the complex planning process. And then, you know, supervised fine-tuning teaches the imitation. Reinforcement learning can teach the model to explore and discover what makes it a really good plan. And then we transfer everything here from the Titan in our little David. This is it. So what we do, supervised fine-tuning, reinforcement learning, DPO, GRPO, we will have a look at this in detail. And you know what is beautiful? Now those reasoning traces are baked into the model weights via a post-training. This is not anymore a chain of thought that we have here in in-context learning, but this is now an inherent part of our little 1 billion, 3 billion, 8 billion. Now, let's increase the complexity. You are brilliant. You are excellent. And as a subscriber of this channel, you know that here in this video, this is the thumbnail here, we looked here in detail that supervised fine-tuning is fundamentally doing the same thing as a DPO. It is optimizing an implicit reward function. And we both looked here in my video here on this new paper that tells us that the implicit reward models tend to generalize worse, especially if we have out of distribution. You might say, okay, following now the mathematics that I showed you here in this video where we had a look at this particular row function, and we could understand if we look here at the single gradient ascent function steps, why this is the case, you might say, you know what? This is great. So if we understand that here our imitation learning process that was in the old times before we become so intelligent was just supervised fine-tuning. So we were just copying the expert. This is no longer true because SFT in the new mathematical fusion framework is now find and maximize an implicit reward function. This is what we call now supervised fine-tuning as an RL functionality. And you said, yes, because in the video that I showed you here, we found that DPO is not just an imitation learning here with a Kullback-Leibler F divergence here in the term. Of course, we have the preference pairs, but you know in this video I showed you a grand unified theory where we combine supervised fine-tuning and reinforcement learning into one new unified theory. And in this theory, we found the DPO is here beautiful. Here, this is our Kullback-Leibler terms. And this is really baked into it. So DPO objective is equivalent to optimizing here an implicit reward model. So suddenly we are faced here with supervised fine-tuning and DPO with two implicit models that are not as good. They do not have the performance because you have seen my video from 2 days ago. So therefore, remember we're looking here at this paper. This was from Carnegie Mellon University about the reasoning transfer capabilities of LLM. And then here, the 15th of June 2025, we looked at this paper with the unified view of supervised finding on DPO connections. And we came to the conclusion that if we now integrate today's main paper, and this is here July 10th, 2025 from Google, and they want to have this post-training language model now, this complex problem solving that we learn from the Titans and we transfer it. Now the problem is, how do we do it? And did Google choose here an implicit reward model or an explicit reward model that has a better performance as published here just 2 days ago? But you know, the main point before we answer this question is what we do, what we achieve. We have now a new approach that shifts here the planning process for the human task from an inference time prompting optimization, like this old grandfather chain of thought idea, now into the parameterized knowledge of our small language model. This is important. We don't waste time at inference and test time training, but we bring it down to the parametric knowledge of the small language model. And of course, it has to learn this, because simply just giving it more time, a small language model will not get more clever with time. So, what a coincidence, Google decided to go with GRPO and not with DPO. And you say, hey, wow, how could Google know this? This was just published 2 days ago. And the study by Google was, I think, in the working for months. Well, what a coincidence. No, sometimes the best results are not immediately published. So GRPO, if you're not familiar, Generalized Reward Policy Optimization. This is from our 2017 PPO paper here from OpenAI. GRPO uses here a scalar numeric reward function beautifully, and the beauty is it is an explicit numeric reward, so Google did everything right. Google read the last paper here from the last 2 days and understood an implicit reward function would not bring the performance, and they went here not with DPO but with GRPO. Reward function is fully explicit. It's actually a fundamental gradient policy approach, and here you have the simple formula. Great. Yeah, if you're not really into mathematics, I have a special video, 52 minutes, my goodness, where I explain AI mathematics in the easiest way you can imagine, and then you just laugh at those formulations. Now let's have a look here. We're going to work now with the surrogate objective function. And you say, hey, wait, I have another name. Yes, it's known as policy surrogate, policy gradient surrogate, objective estimate functions, or some say eclipse surrogate objective function of GRPO, which is of course incorrect, because if you want to be correct, you say a normalized clipped surrogate objective function of GRPO with a Goldberg-Leiber regularization, but you know this. So back to mathematics, this is it. This is our expectation over the sampled rollers and then on average over the timestamps. And if you're still new to AI, no problem. I have you. Here I explain you each and every term, or you just have a look at my other videos. Great. So this means J is now our surrogate objective and approximate. Look at this word, approximate. Trust region stabilized, expected return estimate that is designed, manually designed, to yield practical, low variance, safe gradient updates. And you might say, my goodness, this sounds we really constructed something here that is a little bit, let's call it artificial. This is not a normal mathematical evolution. No, we clip it, we regularize it. We have here absolutely here a base pre-trained model here as the reference model. We have a Goldberg-Leiber divergence that here compares to probability distribution in a rather complex way. We force it to stay to the old policy model. We don't allow big steps, we only allow baby steps. And you might say, this is the future of AI? Well, welcome to the main paper now. So let's start. This was just the introduction. This was the warm-up. Now you know what we are talking about. Now we jump into the topic. July 10, 2025, Google, main paper, go. What they say, okay, we have our titans, we have our GPT-5, whatever, we have the planning trajectory for a particular human task, we extract this, we have a plan verifier, we look at the plans, we say, hey, this is the best plan, we have the plan execution, then we answer this, we have here, then we judge it, say, hey, this is the one, so we have now the perfect optimal trajectory for creating training data. Yes, of course. We have to generate data sets for the training, for the supervised fine-tuning and reinforcement learning of our small language model. Now look at this. This is all that Google gives you here. This is here my complete introduction. Now tell me which one do you prefer, and be aware that I listen to you. So here we go. Plan tuning now, this new approach by Google has two complementary training paradigms. Now, you know both, no? Supervised fine-tuning, clear, beautiful. But now we have here a tuple that includes the input, the plan, the execution, and the answer. And here we have now, from supervised fine-tuning, also two variants, method 1 and method 2. I will explain both in a minute. And then we have the classical reinforcement learning. We go here with explicit reward model. Good move, Google. Beautiful. And we do here an optimization, a little bit of an advanced variation of GRPO. We have a plan GRPO because we want to extract here the planning documentation from the Titans model from GPT-5. And we want to have here this here if an imitation learning process starts injected into our small 1 billion trainable model. Policy gradient optimization rewards both two factors, both the plan quality and the answer correctness. So careful now, when we have here two parameters where the reward will depend upon, amplifying here the high value trajectories while regularizing here the drift here of the complete complex. No, it's not really complex, it's still here in the real world. probability distributions were a Kullback-Leibler penalty. Great. If you want it a little bit easier, simple, supervised fine-tuning seeds here the model with a strong prior here on human-like chain. You notice supervised fine-tuning and chain of thought, linear chains, A, then B, then C, and reinforcement learning refines here towards trajectory that has been extracted here from our titans that empirical yield correct answers on challenging benchmark data. Back to mathematics. M1, method 1 here. The full complexity of a joint supervised fine-tuning, you have here the formula and you see immediately, oh great, tau 1, the human provided plan is a sequence of operators. Then we have here the execution token in position number 2. Then we have the final answer given. And of course we have here the human input. This is my query that I have to the LLM. And the insight is a jointly fitting plan execution and answer ensures end-to-end consistency. But, and this is a big but, you get it right, can dilute here the learning signal for planning when the execution or the answer loss dominates. So the more parameter you have in a complex loss function, they can interplay, cross-overlay. So this is not really the best one. Therefore, we go with the method 2, the plan only. So we say, hey, forget all about the right answer and whatever. We just want, give us the central piece of intelligence, the core of intelligence. If I have a problem, how can I solve it? Give me the plan to the solution. So ignore everything, the execution, the answer, and the loss function. We just have here a focus on the plan. And this is here simpler, faster, more precise. Great. This was supervised fine-tuning, but I told you also we have here a GRPO for the reinforcement learning, and we have a planned GRPO that is depending on 2 parameters. And you might say, oh my goodness, this will be now a real complex topic, and I know you are not gonna believe me, because I hardly believed it myself. So I have here a screenshot from the paper of Google, and this is it. So for the planned tuning GRPO training, we define now here the combined reward from the complexity of the overlapping structure as or plan plus or answer. And you say, what? This is it? Well, yeah, sometimes you make an approximation, so this is it. Google, I love it. So we have here our plan, the plan quality score produced by our similarity function. We'll show you this in a second. And here, the reward here from the answer. And you're not gonna believe what they went, a real complex system, they went with a binary correctness indicator. And you say, oh, you are joking. No, this is why it's a screenshot. So they go with 2 if y matches here the goal, the correct answer, the golden truth, or with 0 otherwise. So this is either 2 or 0. I mean, it's unbelievable. This is simple squared. I'm loving it. And of course you say, okay, now our plan, yeah? You know what they do? They use Gemini to have here the similarity. They say, come on, why should we calculate this? We have a beautiful Gemini 2.5 Pro, super heavy, whatever, when you see this video. So let's use AI for the similarity. So we get here numerical value that is within the interval of 0 to 1. And you might say, this is it? Yeah, this is it. And here in the implementation, they started with Gemini 2.0 Flash. So even cheaper, even older. Unbelievable. And then here you have again the complete flow. Short summary, repeat. This was the question I have. Then the plan we have from our Titan models, from our GPT-5, from O3 Pro, super heavy plan output execution, filtering. We just take the best plans. We just have here the best answers. We have the supervised fine-tuning. We have the reinforcement learning training. Beautiful. So what are the results? There's a lot of other paper here in the other results and numerical data in the paper. Please read the paper yourself. I just give you here the result. JAMA 3, a small little language model if you want, out of domain generalization capabilities. 3 supervised fine-tuning. The baseline, the vanilla supervised fine-tuning, achieves, never mind, on an Olympic bench, a benchmark 31%. Method 1, the joint supervised fine-tuning that I showed you, goes from 31.4 to 32.2. And the plan only, the M2 methodology of supervised fine-tuning, where I said we just focus on the plan only, wow, it even improved further to 34.27. Now, however, if you look at this and say, listen, what we did here. So I have a vanilla supervised fine-tuning at 31.4. And what I achieve after all of this from Google, I have the max 31.4 to 34.2. This is AI research. And then Google tells us, hey, the real reason behind the higher performance here of the plant-tuned models is that this supervised fine-tuning provides you a clear template, the reasoning plans. No? They are very specific, very detailed, very, very specific to the given task. Templates for breaking down a complexity down into multi-step solutions improves. Therefore, they have kind of a highly adaptive blueprint for a structured decomposition, our little David small language models. There is kind of an inconsistent in the paper. Careful, watch out if you read it. For the supervised fine-tuning of the plant tuning methodology, whatever we are just talking, they use here a gamma 3 12 billion instruction trained and a QN3 8B. So this is a 12B is not really a small for me, but okay. But, and here's the big but again, for the GRPO plant tuning, they use the gamma 3 1 billion. Now, 1 billion to 12 billion, this makes a difference. Here the size really makes a difference, so careful. If you read the data, always keep in mind supervised fine-tuning 12, GRPO 1 billion. And 1 billion is really a tiny model, no? This is here, I don't know, for your Apple Watch or something. Yeah, great. So, knowing this, so here GRPO, we are now gamma 3 1B. Plan GRPO, what we do. The performance data. We go here for an in-domain, if you want, benchmark. It goes from the classical vanilla GRPO, let's say 20% to 28%. So for the 1B model, instead of the 20, now it has 28%, plus 8%. Now I'd say, okay, but what about out of domain data sets? The AIM 24. The really interesting aims, no? For gamma 3, we have a better generalization. And whenever I see the text that Google writes, we have a better generalization and no numerical benchmark data, you know you have to be careful, no? And then they say, however, for the QN3 models, we are seeing a performance drop for AIM 24. Now this is interesting, eh? Why? And then they give you the reason training with GRPO is highly dependent on the reward functions. Hey, wait a minute, we want to have a deep dive. So here we go. So here at first, let's have a look at gamma 3. So here these two Olympiad bench and AIM 24. This is our out-of-domain generalization benchmark that we look at. Yeah? So here we have our M1, the M2, and then the planned GRPO, our models that we talked about here, the last 3 rows. But of course, we have the vanilla or the baseline supervised fine-tuning and GRPO as a benchmark. Now, if you tell me that if you have at AIM 24, a GRPO is a 1 billion model and the performance is 0.0%, and then a significant improvement is happening if we go here with a plan GRPO and we achieve now 3%. I don't know if you can call this a significant improvement. So you go from 0 to 3%. So, well, okay, let's say we accept this. Yeah? So, but careful if you listen here to the semantic interpretation. Have a look at the training data and you'll see the truth. But of course, you can have a look here at, let's say here at the Olympiad benchmark. Yeah? Supervised fine-tuning is 31.4, and now with the M1 methodology, with this beautiful new, real complex new construct, we go from 31.4 to 32.2. And you say, okay, but here we have the plan. No, M2 is plan only. You remember, we have seen this exactly. Now we move here from 31 to 34. And you say, yes, congratulations, plus almost 3%. Not really, but yeah, let's say 3% improvement. Yeah? So careful if you see a significant improvement. Sometimes it's rather, Let's look at Q1 3. You remember Q1 3 is now at 4 billion. So we're from a 1 billion to a 4 billion. Now things should start to move. Yeah, but it's moving in a complete different direction. Why? Look at GRPO. Q1 3 4B, vanilla GRPO here, AIM24, 17.7. This is really good. If you compare this with a Gamma 3 with 0, this is really good in the same performance because it is 4 times as big, the model. So you see, size matters. But then look, if we apply our planned GRPO, we fall in the performance from 17.7 to 15.2. So this is now a real relative benchmark interpretation of what is good, what is a significant improvement from 0 to 3, or what is from 17 to 15. Those little tiny models, 1 billion, 4 billion, if you give them rather complex tasks, I have my doubts currently that you can really train them to be better in the reasoning process and in the solution finding process just by providing different plans. Now, you know, Olympiad benchmark, rather simple mathematics, AIM24, real simple mathematics. So we are here really at a level of this is simple, really absolute simple math. No? This is nothing on higher dimensional mathematics. But yeah, those little LLMs, they struggle. It is interesting here, an example. And my goodness, I forgot here the code. So they have a question. Oh, this is my question. Oh, whatever. And then if we only have supervised fine-tuning on reasoning and answer, then this is what will be generated here by the LLM, by the small LLM. So you see, yes, it will follow here this chain of sort reasoning linear trace, but it will have a final answer that turns out to be wrong. No? And then they have here on the other side, if we do here the plan-tuned modeling that we are just talking about here in this video, and they say, listen, if we extract here the plan, so the main idea how to solve this from the big titans, GPT-5 and so on, and we have learned it, so we know that for this particular problem, this particular plan, 24,499, is the correct plan to solve this task. We have it, then we just execute it. Now, remember the reduction of complexity is essential to finding here the best solution. And here, if we know what to do, we know the steps that we have to do, because they are coming from GPT-5, for example, the complexity for the execution for this small language model is now much easier to be done because it just follows here 1, 2, 3, 4, and it just quotation mark fills in here the numerical values and performs the operation plus, minus, and whatever. It could, of course, use here a tool, but we just want to see the inherent parametric knowledge of this. And plan execution comes to the correct answer. Nice, beautiful, love it. Focusing on a plan, highly effective, and you already see what a simple chain of sort argumentation and a supervised fine-tuning was not able to provide. A higher dimensional planning structure that we extract from a GPT-5 provides here much deeper, better strategic reasoning. Now, from the conclusion of the original paper, I have here a quote for you. And I just want to show you this, and I love Google and I love everything they do, of course, but sometimes you have to be a little bit careful when you read them, eh? Because they say across 2 in-domain data sets, so this is here the first column here, this plan-tuned model achieved here an average 7% accuracy boost. Okay, I'm with you, we are here at 81%, and here with a Gamma 3 we have 86% supervised fine-tuning. It's not really 7%. Oh no, we have to look at the Q1. So we go from an 80 to an 87. So yeah, this is also less than 7%. So about 7% accuracy. So yeah, we find it in the data, about 7%, but this is in domain. But we are not interested in domain. We want to have an out of domain benchmark. No, we want to have the real complex stuff. We want to have generalization. We want to have, we want to have more. So out of domain, those 2 columns here, they significantly improved their performance. And again, if you go from 0 to 3%, significantly improved the performance. And if you just use another model, you decline with your performance. So a little bit careful if you read your conclusion, always look at the data. And of course, in a 1 billion model, no, this is really, really tiny for AI. Just to give you an idea, no, this is about the size of an LLM that we use normally. And then here you have a Gamma 3.1b, a little dot, little yellow dot here on your screen. No, this is not a fly, this is a yellow dot. This is all there is on intelligence. No, there's nothing more. So yes, there is a difference between the blue LLM and the little yellow LLM. Yeah? You cannot transfer the complexity in full-fledged hyperscale to this little yellow dot. I think interesting is here, and this is now my personal end of video comments, commands, ideas. Chain of thought, no? Chain of thought, our linear sequence of ideas that included everything, strategic, analytical, performance, whatever. It was the beginning, but now more and more we are going to higher hierarchy of reasoning. And I think this plan tuning, if you close one of your eyes, you'd say, okay, this is something now, the next stage after a chain of thought, a linear chain of thought. The plan tuning is here kind of a strategic plan, how to do this. It is, if you look at detail and you compare it, it's really fundamentally different here from a chain of thought. It's much more complex, and it provides a complete guidance to the solution. Chain of thought for this problem is this. But with plan tuning, what we're seeing today, if you really have here the extraction of a GPT-5, here this plan, no? As easy as it is for a human, for a small language model, a 1 billion model, no? If it has this template to help, no? Calculate the total cost, calculate the increase in value, calculate the new value of the house, calculate then the profit. If it has this as a construct where it can go from step to step and knows exactly what to do, it is so much easier, and there's a higher probability that if you apply a next generation token prediction model here, that this will do a better job than pure chain of thoughts. So, nice idea, Google, but in the implementation complexity, we have to do more better. What is the real advantage that I see on the paper? This plan first idea. You get a complex problem from a human. And then, as an AI, you don't start immediately to try whatever comes to your mind to the first second in your thought. No. You sit down, you analyze here the query, the complexity, you try to understand it, you try to rewrite it, you try to find what are the important steps here from my parametric knowledge. Maybe you have to go to graph RAG or any other RAG that you know, reasoning RAG or multi-agent RAG. Find other solution, compare the different solutions that you as an AI found here from the internet, what you have internal knowledge, and then design the best plan for you given here this specific human query. So you see this plan also acts as a guardrail from preventing the model here just going off here the logical path. And it is another, if you want, Kullback-Leibler divergence here on a meta level to bring it down so that our probability distribution from next token prediction stays somewhere close and not just go crazy into configuration space or into solution space. And there you have it. This is the video of today. I hope you enjoyed it. So steal the genius plan from the Titans. And if you had little small language model, yes, there's a way forward. Are we there yet? No, we have a lot of work to do. But I think it's going to be fascinating the next month of AI. New methodologies to be developed, new models to be trained. Because remember, all the models that will come out, Gemini Pro 3, they have all been trained on the old methodology. In the new methodology, none model has been trained yet on this new one. So, AI looks absolutely beautiful in the future. If you want to see more, subscribe. I see you.